What if everything we think we know about the universe is just the surface of something far stranger? Picture standing at the edge of an endless cosmic ocean, where the waves you see aren't made of water but of invisible forces, hidden dimensions, and structures so vast they bend reality itself. This isn't science fiction, it's the cutting edge of what science is uncovering right now. For centuries, we've mapped the stars, measured galaxies, and pieced together the laws of physics, only to stumble upon mysteries that defy explanation. Dark matter weaving through space like ghostly threads, black holes warping time, and quantum particles that seem to dance between dimensions. These aren't just oddities. They're clues pointing to a hidden architecture beneath the universe, waiting to be decoded, and that's where things get thrilling. Behind the curtain of the visible cosmos, there are theories, some bold, some bizarre, that attempt to explain the unexplainable. Imagine a universe built like a hologram, where everything you see is just a projection from the edge of space. Or consider the idea that our entire cosmos is one tiny bubble in an endless froth of parallel realities, each with its own laws of physics. These aren't wild guesses, they're serious scientific explorations born from the minds of physicists daring to ask, what if we're missing the bigger picture? That's exactly what we're diving into today. Over the course of this journey, we'll uncover 30 of the most fascinating theories about the universe's hidden structures, ideas that challenge everything from gravity to the very nature of existence. Some will sound like pure magic, others like revelations waiting to be proven, but each one offers a glimpse into the profound mysteries that still puzzle the brightest minds on Earth. So if you've ever looked up at the night sky and wondered what secrets it's keeping, you're in the right place. Buckle up, we're about to venture into the unknown. The first theory we're exploring might just bend your understanding of reality itself, the holographic principle. At its core, this idea suggests that everything we experience, the three-dimensional world with its galaxies, planets, and even you watching this, could be nothing more than a projection. But not from some futuristic projector. Instead, think of the entire universe as a hologram, where all the information needed to construct our reality is actually encoded on a two-dimensional surface at the very edge of space. This isn't just science fiction. The holographic principle emerged from one of the most perplexing puzzles in physics: black holes. When matter falls into a black hole, it seemingly vanishes, but physics has a rule: information can't be destroyed. So where does it go? In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking discovered something astonishing. They realized that the information about everything swallowed by a black hole isn't lost, it's imprinted on the black hole's event horizon, the point of no return. That boundary, a two-dimensional surface, somehow holds a complete description of all the three-dimensional objects that fell in. That revelation sparked a wild question: what if the entire universe works the same way? If a black hole's 3D contents can be perfectly encoded on its 2D surface, could our cosmos be just a projection from some distant, flat boundary we can't see? This idea gained traction when theoretical physicists like Leonard Susskind and Gerard T. Hooft expanded it beyond black holes, proposing that space itself might operate like a cosmic hologram. Imagine holding a credit card. The hologram on it looks three-dimensional, but it's actually stored on a flat, two-dimensional strip. Now scale that up to the universe. Every star, every atom, every thought you've ever had, could all of it be written on some vast, unseen surface we'll never touch? It's a dizzying thought, but the math checks out. The holographic principle even helps solve some of the biggest problems in physics, like unifying quantum mechanics and gravity. Yet the implications are even stranger. If this theory is true, it means reality isn't just out there. It's a kind of illusion, an incredibly detailed shadow cast by information we can't perceive directly. It challenges the very idea of depth, suggesting that what we see as volume might just be a trick of the cosmic light. Could we ever prove it? Some scientists are looking for evidence in the faintest whispers of the cosmos, tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang. Others are exploring quantum entanglement, where particles separated by vast distances behave as if connected, hinting at a deeper, hidden layer of reality. For now, the holographic principle remains just that, a theory, but it's one that forces us to rethink everything we assume about space, time, and the nature of existence itself. And if it's right, it means the universe isn't just stranger than we imagine, it's stranger than we can imagine. Now, let's step into a universe threaded with invisible scars, cosmic strings, remnants of the universe's fiery infancy. Picture the cosmos right after the Big Bang, a seething cauldron of energy and forces colliding, cooling, and settling into the fabric of spacetime. But like cracks forming in ice as it freezes, spacetime itself might have developed flaws, one-dimensional defects thinner than an atom yet stretching across the entire universe. These are cosmic strings, hypothetical filaments of pure energy, so dense that a single inch could weigh more than a mountain. If they exist, cosmic strings would be anything but ordinary. Unlike black holes or stars, they wouldn't have endpoints. They'd either form infinite lines or loop back on themselves, weaving through the cosmos like invisible spider silk. And their gravitational pull would be so intense that they could warp space around them, bending light and creating double images of distant galaxies. Imagine looking at a star and seeing its twin right beside it, not because there are two stars, but because a cosmic string's gravity is acting like a lens, distorting the very path of light. But the strangest possibility, cosmic strings might not just bend space, they could twist time. Some theories suggest that if two strings crossed or a loop collapsed, they could create closed time-like curves, effectively forming time loops. Yes, you heard that right, regions where time circles back on itself. It's the stuff of science fiction, but mathematically, it's plausible. Picture a spaceship traveling around a rapidly spinning cosmic string. Under the right conditions, it might return to its starting point not just in space, but in time, arriving before it even left. These bizarre threads could also be cosmic detectives, helping us uncover the universe's secrets. When cosmic strings move or vibrate, they'd send ripples through space-time gravitational waves. Unlike the waves from colliding black holes, these would carry a distinct fingerprint, a steady hum in the fabric of the cosmos. Scientists are already listening for them with detectors like LIGO, hoping to catch a whisper from these primordial relics. Yet the wildest part, cosmic strings might be hiding in plain sight. Some theories propose they could explain mysterious gaps in the cosmic microwave background or even the uneven distribution of galaxies. If we ever find one, it would be like uncovering a fossil from the universe's first moments, a direct window into the forces that shaped everything we know. So while cosmic strings remain theoretical for now, their potential to rewrite physics is undeniable. From bending reality to unraveling time, they remind us that the universe's hidden structures might be far stranger and more tangled than we ever dreamed. What if our universe isn't the only one, not just in science fiction, but as a fundamental feature of reality itself? This brings us to one of the most mind-bending theories in modern cosmology, the inflationary multiverse. Picture the aftermath of the Big Bang when space didn't just expand. It exploded outward at speeds faster than light itself, stretching the fabric of reality in a process called cosmic inflation. Most cosmologists agree this happened, but here's where things get wild. If inflation didn't stop everywhere at once, it could still be happening right now in distant regions beyond our observable universe, endlessly birthing new cosmic bubbles like foam in an infinite ocean. Each of these bubbles could become its own self-contained universe with its own unique physics, constants, and even dimensions. In one, gravity might be stronger, making stars burn out in moments. In another, atoms might never form, leaving only swirling energy. Some could harbor life stranger than anything we've imagined, while others might be barren voids. This is the level I multiverse, not parallel worlds in some sci-fi sense, but natural outcomes of inflation's unstoppable expansion, each universe forever separated from the others by unimaginable distances. How could this happen? Think of boiling water. As it heats, tiny bubbles form, expand, and collide. Now imagine space itself is that boiling water, with inflation driving the process. Our universe is just one bubble that stopped inflating, allowing matter and galaxies to form. But elsewhere, the process continues, creating an endless array of realities where even the laws of physics might differ. This isn't pure speculation, it's grounded in the math of inflationary theory. When quantum fluctuations during inflation get stretched across space, they could seed entirely separate universes, each with its own random arrangement of particles and forces. The implications are staggering. If true, it means every possible variation of reality exists somewhere in this infinite ensemble. A version of you might be reading this script in a universe where dinosaurs never went extinct or where Earth orbits a blue sun. But here's the catch: we'll never see these other universes. They're beyond our cosmic horizon, receding faster than light could ever bridge the gap. Yet their existence could explain one of cosmology's deepest mysteries: why our universe seems so finely tuned for life. If every possible physics plays out somewhere, it's no surprise we find ourselves in a bubble where conditions allow us to exist. Could we ever prove the multiverse? Some scientists search for imprints of bubble collisions in the cosmic microwave background, like bruises from neighboring universes bumping into ours. Others look for anomalies in the distribution of galaxies that might hint at edges where our bubble meets another. For now, the multiverse remains a tantalizing possibility, pushing us to confront the humbling idea that everything we know might just be one page in an infinite cosmic library. But what if the multiverse isn't just bubbles in an inflating cosmos? What if entire universes exist with different laws of physics where gravity, light, even the number of dimensions aren't just variations but entirely new realities? This is where the idea of the multiverse gets even wilder, with string theory's landscape of possible universes. Unlike the inflationary multiverse, where bubbles share the same fundamental rules, this version suggests that the very constants of nature, the numbers that make our universe work, could be shuffled like a cosmic deck of cards elsewhere. At the heart of this theory lies string theory's most provocative claim: that the universe might have 10 or 11 dimensions, with all but the familiar 3 of space and 1 of time curled up so tightly we'll never perceive them. But here's the twist: the way those extra dimensions fold and vibrate could determine everything from the strength of gravity to the mass of an electron. And if those dimensions can take different shapes, then each configuration would create a universe with completely different physics. Picture a library where every book isn't just a variation on the same story, but written in a unique language with its own rules of grammar. That's the string theory landscape, a vast, perhaps infinite, array of possible universes, each with its own blueprint for reality. This isn't just abstract math. It could solve one of science's greatest mysteries: why our universe seems impossibly fine-tuned for life. Change the strength of gravity by a fraction, and stars might never form. Tweak the charge of an electron, and atoms couldn't bond. It's like winning the cosmic lottery, except if the multiverse contains every possible set of rules, then of course we'd find ourselves in one where life is possible. This is the anthropic principle in action: not why our universe is hospitable, but that we're here to observe it at all. Some scientists take this further, suggesting that string theory's landscape could contain 10 to the 500 possible universes, a number so large it dwarfs the atoms in our observable cosmos. In such a scenario, every conceivable combination of constants would exist somewhere, from universes where time runs backward to ones where dark energy crushes reality into an instant. Could we ever test this? It's a challenge, but some theories suggest clues might hide in the cosmic microwave background, subtle fingerprints of collisions with other universes or anomalies in the distribution of matter. Others propose that advanced civilizations might one day engineer experiments to probe these extra dimensions directly. For now, the string theory multiverse remains a breathtaking what-if. But it forces us to confront the staggering possibility that our universe isn't just one possibility, it's one page in an endless catalog of realities, each playing by its own rules. And if that's true, the search for understanding just got a lot bigger. Now let's take the multiverse idea to a place even stranger, where reality splinters with every choice, every chance, every quantum flip of a coin. This is the quantum multiverse, or the many worlds interpretation, and it doesn't just suggest other universes exist, it says they're being created constantly, branching off from our own with every possible outcome of every quantum event. Forget bubbles or hidden dimensions. Here, the multiverse is woven into the fabric of reality itself, unfolding in an infinite tapestry of what-ifs. To grasp this, think of Schrödinger's famous cat, the thought experiment where a cat in a box is both alive and dead until someone opens it and collapses the possibilities into one outcome. The many worlds interpretation flips this on its head. There's no collapse. Instead, the universe splits, one world where the cat lives, another where it dies, both equally real. And this isn't just about cats. Every quantum event, an electron's spin, a photon's path, even the firing of neurons in your brain triggers these branches. Missed a bus today somewhere, a version of you caught it, chose coffee over tea, another you sipped the alternative. The math suggests these branches aren't hypothetical, they're inevitable. The origin of this idea traces back to physicist Hugh Everett in the 1950s, who dared to ask, what if quantum mechanics isn't about probabilities but actualities? In his radical view, the universe isn't probabilistic, it's deterministic, with every possible outcome playing out in its own timeline. No randomness, just a cosmic tree with infinite branches, each tracing a unique path. But how could this work? Imagine reality as a river constantly forking into new streams. At the quantum level, particles exist in superpositions, multiple states at once. Traditional physics says observation picks one state. Many worlds says all states happen. We just perceive one while other versions of us perceive the rest. It's like flipping a coin and seeing heads, while another you in another world sees tails, both outcomes real, both universes equally valid. The implications are staggering. If true, there's a universe where dinosaurs still roam, where the Roman Empire never fell, where you made every possible life choice. It also solves one of quantum mechanics' biggest headaches, the measurement problem, by removing the need for observers to collapse reality. Instead, reality never collapses, it just keeps expanding. Critics argue this is untestable since these branches can't interact. But supporters point to quantum experiments like the double-slit test, where particles behave differently when observed. In many worlds, that's not mystery, it's just other branches influencing outcomes. Some even suggest that if we could build a quantum computer powerful enough, it might leak information from parallel timelines, offering indirect proof. Whether real or not, the many worlds interpretation forces us to confront a humbling truth. The universe might not just contain alternate realities, it might be them, endlessly dividing like cells in a cosmic organism. And somewhere out there, another version of you is still pondering this very idea, just with a different ending. We've explored universes hidden in dimensions and timelines, but what about the shadowy skeleton holding our own cosmos together? Enter dark matter halos, the ghostly frameworks that shape everything from galaxies to the largest structures in the universe. Picture a spiderweb so vast it spans millions of light years, its strands invisible except for the way galaxies cling to them like dewdrops. That's dark matter, an enigmatic substance that doesn't emit light, absorb it, or interact with ordinary matter in any way except through gravity. Yet without it, the universe as we know it would unravel. Here's the mystery. When astronomers measure the rotation of galaxies, they find stars orbiting at speeds that defy the laws of gravity, unless there's 6 times more mass than what's visible. That missing mass, dark matter, swirling around galaxies in vast, diffuse halos that extend far beyond their luminous edges. These halos aren't just passive backdrops, they're cosmic architects. In the early universe, slight clumps of dark matter acted as gravitational seeds, pulling in gas and dust to form the first galaxies. Without these invisible scaffolds, stars might never have ignited. But what is dark matter made of? Among the leading candidates are WIMP, weakly interacting massive particles, hypothetical heavy particles that barely touch ordinary matter except through gravity. Think of them as cosmic phantoms drifting through your body right now by the billions without a trace. Then there are actions, ultra-light particles born from theoretical fixes to quantum physics, so tiny they behave more like waves than particles. Some experiments hunt for WIMP in underground labs, shielded from cosmic noise, waiting for the rare ping of a collision. Others use powerful magnetic fields to coax actions into revealing themselves. The strangest clue, dark matter halos might not be smooth. Simulations suggest they're lumpy, with dense subhalos lurking within larger ones, like shadows within shadows. Some researchers even propose these clumps could host dark stars, theoretical objects powered by dark matter annihilation instead of nuclear fusion. Yet for all our tools, dark matter remains elusive. Its particles might be too exotic for current detectors, or we might need entirely new physics to explain it. One thing's certain, solving this riddle wouldn't just reveal the universe's hidden bones, it would rewrite our understanding of reality itself. If dark matter is the invisible scaffold of the cosmos, then dark energy is the mysterious force tearing it apart. Imagine blowing up a balloon with galaxies drawn on its surface, except the balloon keeps inflating faster and faster. Not because of anything inside it, but because of something woven into the fabric of space itself. That's dark energy in action, an enigmatic pressure causing the universe's expansion to accelerate, stretching the distances between galaxies with no signs of slowing down. The discovery of dark energy shook astronomy to its core. In the late 1990s, 2 teams of scientists were measuring distant supernova, expecting to find the universe's expansion slowing under gravity's pull. Instead, they found the opposite. The cosmos was speeding up, as if some unseen hand had flipped a switch. The implications were staggering. Either Einstein's theory of gravity was incomplete, or space itself contained a bizarre form of energy that behaved unlike anything known. That energy, now called dark energy, makes up nearly 70% of the universe's total content. Yet to this day, we still don't know what it actually is. One leading explanation points to the cosmological constant, a term Einstein once added and later discarded to his equations to keep the universe static. Revived in this context, it suggests that empty space isn't truly empty, it's seething with a faint, repulsive energy that grows stronger as the universe expands. Picture a vast ocean where every new drop of water creates more waves, pushing everything apart. The catch, quantum physics predicts this energy should be 10 to the power of 120 times stronger than what we observe. A discrepancy so vast it's been called the worst theoretical prediction in history. But dark energy isn't just stretching space, it's sculpting the universe's grandest structures. Across billions of light years, galaxies aren't scattered randomly. They're threaded along immense filaments of dark matter, forming a cosmic web. Dark energy's relentless push shapes this web, determining where galaxies cluster and where vast voids yawn empty. In regions where dark energy dominates, galaxies drift apart like leaves on a receding tide. Where gravity still holds sway, they cling together in superclusters, the last islands of structure in an ever-expanding sea. Could dark energy change over time? Some theories suggest it might evolve, potentially leading to a big rip where even atoms are torn apart, or a big crunch where the universe collapses back on itself. Others propose it's an illusion, a sign that gravity behaves differently on cosmic scales. For now, telescopes like Euclid and the Vera Rubin Observatory are mapping the universe's expansion in unprecedented detail, hunting for clues in the subtle warping of light or the distribution of galaxies. Dark energy remains one of physics' deepest puzzles, a reminder that the universe isn't just expanding, but doing so in ways we're only beginning to fathom. And as it stretches the fabric of reality, it's also stretching the limits of our understanding. Deep in the cosmic void, something invisible is tugging at thousands of galaxies, including our own Milky Way, with a force so immense it defies explanation. Astronomers call it the Great Attractor, a gravitational anomaly lurking roughly 250 million light-years away in the direction of the constellation Centaurus. But here's the catch: we can't actually see it. This mysterious behemoth hides behind the Milky Way's dense band of stars and dust, a region so obscured by cosmic clutter that scientists nicknamed it the zone of avoidance. It's like trying to spot a lighthouse through a hurricane, except this lighthouse might rewrite our understanding of the universe's largest structures. The first clues emerged in the 1970s when astronomers noticed something odd. Galaxies across our local supercluster, including Andromeda and our own, were all streaming toward the same patch of sky at breakneck speeds, as if being pulled by an unseen hand. Calculations suggested an immense mass, equivalent to tens of thousands of Milky Ways, was responsible, but the zone of avoidance blocked direct observation, leaving researchers with only indirect measurements and gravitational breadcrumbs to follow. One leading theory points to the Norma cluster, a dense gathering of galaxies near the suspected epicenter, as the heart of the Great Attractor. But there's a problem: it's not nearly massive enough to explain the observed pull. That discrepancy fueled wilder ideas. Perhaps it's a supermassive black hole of unimaginable scale, or a knot of dark matter so dense it warps the fabric of spacetime itself. Then came an even bigger twist. In the 2000s, deeper sky surveys revealed that the Great Attractor might just be a waypoint on a far grander journey. Beyond it lies the Shapley supercluster, the most massive known structure in the local universe, a sprawling metropolis of galaxies with gravity powerful enough to reel in entire superclusters like fish on a line. Could the Great Attractor simply be a middleman in this cosmic tug-of-war, or does it hide secrets we've yet to uncover? The mystery deepens with every new observation. Some models suggest the Great Attractor isn't a single object at all, but a confluence of dark matter filaments, the hidden scaffolding of the universe bending the paths of galaxies like rivers converging at a delta. Others propose it's evidence of exotic physics, where gravity behaves differently on scales larger than we've ever tested. For now, penetrating the zone of avoidance remains a monumental challenge. Infrared and radio telescopes peer through the dust, mapping structures normally lost in the glare. Each new dataset chips away at the enigma, revealing not just a destination, but a roadmap of the universe's grandest flows. Whatever the Great Attractor is, one thing's certain: it's pulling more than just galaxies. It's pulling us toward a revelation about the invisible forces shaping everything we know. The universe begins with a bang, or does it? What if instead of a singular, fiery birth, our cosmos has been through countless lives, collapsing and rebounding in an endless cosmic heartbeat? This is the Big Bounce theory, a radical reimagining of the universe's story where the Big Bang wasn't the beginning, but just the latest chapter in an infinite cycle of destruction and rebirth. Picture a rubber band stretched to its limit, then snapping back, except here the rubber band is spacetime itself. In this model, the universe doesn't end in heat death or a big crunch. Instead, as it collapses under gravity's pull, quantum effects near the point of maximum compression create a repulsive force so powerful it reverses the collapse, triggering a new expansion. The result, a universe that dies only to be born again, with each cycle potentially lasting trillions of years. The origins of this idea trace back to the 20th century, when physicists like George Gamow and later Robert Dicke toyed with cyclic models. But the modern Big Bounce gained traction thanks to breakthroughs in loop quantum gravity, a framework that suggests spacetime is granular at the smallest scales, like a fabric woven from tiny, indivisible threads. These quantum grains, the theory proposes, could resist infinite compression, creating a bounce instead of a singularity. Imagine squeezing a sponge. At some point, it can't compact further, and the pressure forces it to spring back. That's the universe in this scenario, a cosmic sponge eternally rebounding. But there's a glaring problem: entropy. The second law of thermodynamics states that disorder always increases, meaning each bounce should leave the universe more chaotic than the last. So how could cycles continue indefinitely without degenerating into total randomness? Some theorists suggest that entropy might reset during the bounce, effectively erasing the universe's accumulated disorder. Others propose that the laws of physics themselves could evolve with each cycle, allowing for fresh beginnings. The implications are profound. If the Big Bounce is real, our universe might carry faint echoes of its predecessors' patterns in the cosmic microwave background, anomalies in the distribution of galaxies, or even remnants of ancient black holes lingering like fossils from a prior cycle. Some models even suggest that the fundamental constants of nature could shift slightly with each rebirth, meaning the laws of physics might not be eternal but cyclical. Yet the biggest question remains: could we ever prove it? Detecting evidence of a pre-Big Bang universe would require breakthroughs in quantum gravity or unexpected signatures in gravitational waves. For now, the Big Bounce remains a tantalizing what-if, a reminder that the universe's story might not be linear but an epic without end, written in the rhythm of collapse and renewal. One thing's certain: if true, it means the cosmos isn't just expanding, it's breathing. What if the Big Bang wasn't an explosion but a cosmic car crash? That's the startling premise of the ekpyrotic universe theory, where our universe wasn't born from a singularity, but from the collision of two unimaginably vast structures lurking in higher dimensional space. Imagine two sheets of paper floating parallel to each other in a dark room, except these sheets are three-dimensional brains, short for membranes, existing in a reality with more dimensions than we can perceive. According to this radical idea, when these brains smashed together, the energy released didn't just create stars and galaxies, it became them, seeding everything we see today. This theory emerges from string theory's boldest claim, that the fundamental particles of our universe aren't points but tiny, vibrating strings, and those strings exist in a reality with 11 dimensions. Most are curled up so tightly we'll never notice them, but some, like the dimensions separating brains, could be vast. In this framework, our entire universe might be stuck to one brain, like dust clinging to a tabletop, while other brains hover just out of reach in higher dimensional space. The energy of their collisions wouldn't just mimic the Big Bang, it could explain why the early universe was so perfectly smooth, without the chaotic wrinkles a traditional singularity would leave behind. Here's where it gets wild. The ekpyrotic model suggests these collisions aren't one-time events. Brains could oscillate, periodically crashing and rebounding in an endless cycle, each bang a reset button for cosmic history. Unlike the Big Bounce, where the universe collapses and re-expands, here it's the brains themselves that drive renewal, like cymbals clashing in an eternal symphony. But could we ever prove it? Supporters point to potential fingerprints in the cosmic microwave background, subtle swirls in the afterglow of creation that would look different from standard inflation predictions. Others hunt for gravitational waves at frequencies no single black hole merger could produce, hints of ancient brain-shaking violence. Yet skeptics argue the math is speculative, and the extra dimensions remain frustratingly out of reach. Whether fact or fiction, the ekpyrotic universe forces us to rethink the most fundamental question of all. What if our origins weren't solitary, but shared with realities we can't yet see? It's a reminder that the cosmos might not just be stranger than we imagine. It might be stranger than we can imagine, with collisions in hidden dimensions writing the story of everything. What if everything around us, the stars, the laws of physics, even your thoughts as you watch this, isn't real? Not in the way we assume, at least. This is the simulation hypothesis, the idea that our universe might be nothing more than an ultra-advanced computer simulation created by a civilization so far beyond us, their technology would seem like magic. It sounds like sci-fi, but this theory has deep roots in philosophy, physics, and even Silicon Valley boardrooms, with serious thinkers arguing it's not just possible, it might even be likely. The seed of this idea was planted centuries ago. René Descartes wondered if an evil demon could be tricking us into perceiving a false reality. Plato's allegory of the cave suggested we might only see shadows of the true world. But the modern formulation comes from philosopher Nick Bostrom, who in 2003 laid out a chilling logical trilemma. Either one, advanced civilizations always go extinct before developing simulation technology. Two, they reach that level but choose not to run ancestor simulations. Or three, we're almost certainly living in one. His reasoning hinges on probability. If even one civilization could create countless simulated universes, the number of artificial minds would dwarf biological ones, making it statistically improbable we're in the original reality. But how would such a simulation work? Think of the vast open-world games we create today, with physics engines rendering realistic weather, lighting, and NPC behavior. Now scale that up to an entire universe where every quantum fluctuation, every galaxy's spin, is calculated in real time by some unfathomable computer. At first glance, that seems impossible. The processing power required would be absurd. But here's the twist: the simulation wouldn't need to render every detail at once. Just like a video game only loads the parts of the world you're currently seeing, a universe-scale sim could prioritize active observers, filling in the rest as needed. This quantum observation effect eerily mirrors how particles in experiments seem to behave differently when measured, as if the simulation is conserving resources. Then there are the potential glitches. Some theorists scan reality for anomalies that might betray the code beneath the cosmos, particles popping in and out of existence. Quantum entanglements, spooky action at a distance, where particles instantly influence each other across light years. These could be signs of processing shortcuts or latency in the system. Even déjà vu or the Mandela effect, where large groups misremember events, might hint at patches or updates in the simulation's narrative engine. But the most unsettling evidence might be the universe's mathematical perfection. Why do fundamental constants like the speed of light or the strength of gravity have such precise, life-allowing values? In a simulation, those numbers aren't discovered, they're chosen. Fine-tuning could simply mean the programmers dialed in the parameters intentionally. Could we ever prove it? Some scientists propose crashing the system by overloading it, say, by creating a state so complex the simulation can't compute it. Others look for pixelation in space-time at the smallest scales, like finding the resolution limit of reality. Elon Musk has famously said the odds we're in base reality are 1 in billions. Yet the simulation hypothesis isn't just a technological thought experiment, it's a mirror. If true, it forces us to ask, what's the purpose of the simulation? Are we someone's history project, an AI training ground, or something we can't even conceive? And if we're just code, does that make the beauty of a sunset or the sting of loss any less real? After all, in a universe where everything is information, maybe reality was always virtual, we just didn't know it. Imagine floating alone in the infinite void of space, no stars, no planets, just endless darkness. Now picture a disembodied brain suddenly flickering into existence, complete with memories, thoughts, and the eerie conviction that it's always been part of a real world. This isn't the plot of a horror movie, it's the Boltzmann brain paradox, one of the most unsettling ideas in modern physics. Named after 19th century physicist Ludwig Boltzmann, this thought experiment takes the laws of thermodynamics and twists them into a cosmic hall of mirrors where reality itself might be an accident. The paradox starts with a simple fact: entropy, the measure of disorder in the universe, always increases over time. But entropy doesn't care how it increases, it just follows the path of least resistance. In an eternally chaotic universe, every now and then, particles could randomly arrange themselves into an ordered state purely by chance. Most of the time, that means useless noise, a temporary swirl of atoms. But given enough time, say trillions upon trillions of years, even the most improbable events become inevitable, including a fully formed, self-aware brain popping into existence, complete with fabricated memories of a past that never was. Here's where it gets eerie. If the universe lasts long enough, or if multiple universes exist, there are statistically more ways for a single conscious mind to form spontaneously than for an entire ordered cosmos like ours to evolve naturally. So if you're weighing probabilities, it's far more likely you are that lone, accidental brain hallucinating reality than a person living in a real, structured universe. It's like flipping a coin and getting heads a billion times in a row, technically possible, but so absurdly unlikely that if it happens, you'd assume the coin is rigged. The Boltzmann brain isn't just a philosophical nightmare, it challenges our understanding of time's arrow. Why does time move forward at all? Boltzmann suggested it's because we're in a low-entropy pocket of a much larger, disordered cosmos where fluctuations create temporary islands of order like ours. But if that's true, then our entire history, the Big Bang, the rise of life, even you watching this video, could just be a fleeting blip in an otherwise chaotic eternity. Critics argue the paradox is a reductio ad absurdum, exposing flaws in how we apply probability to cosmology. Others propose solutions. Maybe the universe doesn't last forever, cutting off the time needed for Boltzmann brains to dominate. Or perhaps consciousness can't emerge from random fluctuations, no matter how statistically likely. Some even suggest that if we are Boltzmann brains, we'd lack consistent memories, making the idea self-refuting. Yet the paradox lingers, a ghost in the machinery of physics. It forces us to confront the fragility of our assumptions, not just about reality, but about how we define real in the first place. After all, if a brain can dream up a universe, how do we prove ours isn't the dream? Rising from the heart of our galaxy like twin exhaust plumes from some cosmic engine, the Fermi Bubbles defy everything we thought we knew about the Milky Way's peaceful neighborhood. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these colossal structures stretch 25,000 light-years above and below the galactic center, each one a towering fountain of high-energy gamma rays, crackling with enough power to rewrite the story of our galaxy's past. But what carved these invisible titans into the fabric of space? The answer might lie in a cataclysm so violent, its echoes still ripple through the cosmos millions of years later. One leading suspect is the supermassive black hole squatting at the Milky Way's core, Sagittarius, a star. Normally quiet, this gravitational monster might have awakened in a feeding frenzy sometime in the last few million years, gorging on stars and gas until it belched out twin jets of energy powerful enough to punch through the galaxy's disk. Astronomers call this an active galactic nucleus, or an outburst, a cosmic tantrum that could explain the bubble's symmetrical shape and searing gamma rays. Picture a dormant volcano suddenly erupting, spewing ash so high it reaches the stratosphere. Now scale that up to galactic proportions, with energy blast strong enough to light up half the visible universe. But not everyone's convinced. Some theorists point to the bubble's razor-sharp edges and uniform glow as evidence of something even stranger, dark matter annihilation. If dark matter particles collide and destroy each other near the galactic center, they'd unleash a storm of gamma rays matching the Fermi Bubbles profile. It's a tantalizing thought. These structures might be the first visible fingerprints of dark matter's secret interactions, a shadowy process normally hidden from our telescopes. Then there's the wild card stellar feedback. The Milky Way's core is a factory for massive stars which live fast and die in supernova. Over millennia, these explosions could have pumped enough energy into the galactic halo to inflate the bubbles like balloons. But here's the catch. The sheer scale of the Fermi Bubbles demands energy beyond what even 1,000 supernova could muster. Unless, of course, we're missing something fundamental about how stars shape their galaxies. The debate rages on, but one thing's certain: the Fermi Bubbles aren't just ancient relics, they're active laboratories. Recent observations reveal substructures within them, like nested shells or chimneys, suggesting multiple eruptions or ongoing energy injection. Some researchers even speculate they're linked to the galaxy's mysterious microwave haze, a fog of high-energy electrons that might share the same explosive origin. As telescopes grow sharper and simulations more sophisticated, we're inching closer to solving this puzzle. But whether the answer points to black hole tantrums, dark matter fireworks, or something entirely unforeseen, the Fermi Bubbles remind us that even our home galaxy harbors enigmas vast enough to dwarf the imagination. And somewhere in their ghostly glow, the truth about the Milky Way's turbulent past and perhaps its fiery future is waiting to be decoded. What if the universe we know isn't the vast expanse we imagine, but the interior of something far more unfathomable? Enter the black hole universe theory, a mind-bending idea that suggests our entire cosmos might exist inside a black hole, with every galaxy, star, and planet nothing more than the contents of a gravitational prison from which even light can't escape. It sounds like something ripped from a sci-fi novel, but this hypothesis emerges from a chilling intersection of general relativity and quantum mechanics, painting a picture where black holes aren't endpoints, they're cosmic wombs birthing new realities. The spark for this idea comes from an eerie symmetry in the math. When you calculate the density of the universe at the moment of the Big Bang and compare it to the density of matter collapsing into a black hole, the numbers align almost perfectly. Both scenarios involve all matter and energy crushed into an unfathomably tiny point, a singularity. But here's the twist. While a black hole's singularity traps everything inside its event horizon, what if that boundary isn't the end? What if it's the beginning of a new space-time, curled inward like a cosmic Möbius strip? This isn't just poetic speculation. Physicists like Nikodem Poplawski have explored models where the intense torsion, a twisting force in space-time, at the heart of a collapsing black hole could trigger a rebound like a spring compressed to its limit. Instead of infinite density, the singularity bounces, erupting into an entirely new universe hidden behind the veil of the event horizon. In this scenario, every black hole in our universe could be a doorway to another cosmos with its own physics, stars, and perhaps even life. Our own Big Bang might have been the moment some distant, dying universe birthed us through a black hole's violent transformation. But the implications stretch even further with Roger Penrose's conformal cyclic cosmology, or CCC. This radical framework proposes that the universe doesn't just cycle through black holes, it repeats itself across infinite eons. Here's how it works. As our universe expands toward heat death, all matter eventually decays into massless particles like photons. Without stars or atoms, space becomes a featureless sea of energy. But in this state, the universe loses any sense of scale. A photon traveling for trillions of years experiences no time at all. At this point, Penrose argues, the universe's end becomes indistinguishable from its beginning, resetting the conditions for a new Big Bang. The most stunning evidence for CCC, Penrose claims to have found Hawking points in the cosmic microwave background. Circular imprints, he argues, are the evaporated remnants of supermassive black holes from a previous universe, their energy echoing like ghosts in the afterglow of creation. If true, these faint scars would mean our cosmos isn't the first iteration. It's the latest chapter in an infinite sequence of universes, each birthed from the ashes of the last. Critics counter that CCC stretches known physics to its breaking point, and Hawking points remain hotly debated, yet the allure of these ideas is undeniable. They weave black holes, the destroyers of worlds, into cosmic creators, spinning a narrative where death and rebirth are intertwined on scales beyond comprehension. Whether our universe is nestled inside a black hole or destined to recycle itself eternally, one thing's clear: the cosmos might not just contain mysteries, it might be one, layered like an infinite set of cosmic nesting dolls. Deep in the afterglow of the Big Bang, scientists found something they weren't expecting: a cosmic axis so unnerving they called it the axis of evil. This isn't some ancient prophecy or sci-fi plot twist. It's a bizarre pattern etched into the cosmic microwave background, the oldest light in the universe, that threatens to upend our most basic assumptions about how the cosmos works. Imagine drawing a line through space and discovering that the universe itself seems to have a preferred direction, like a hidden fingerprint of forces we've never seen. The story begins with the Planck satellite, a European Space Agency mission designed to map the CMB with unprecedented precision. Scientists expected this relic radiation, the faint echo of the universe's fiery birth, to be evenly distributed, a random scatter of hot and cold spots reflecting quantum fluctuations from the first moments of existence. But what they found was anything but random. Certain large-scale features in the CMB appear oddly aligned along a specific axis, as if the universe has a subtle tilt. Some patches of sky are warmer, others cooler, and these variations aren't scattered like confetti. They're organized in a way that defies the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. At first, researchers brushed it off as observational noise or instrument error, but the signal persisted, showing up in data from NASA's WMAP satellite and later confirmed by Planck. The odds of this happening by chance, less than 1 in 1,000. It's as if you rolled a die 100 times and kept getting the same number. Something fundamental might be off. So what could explain it? One radical possibility is that the axis of evil isn't a fluke but a cosmic scar, a remnant of something that existed before the Big Bang. Some theories suggest our universe might have collided with another in a higher dimensional space, leaving behind a directional imprint. Others propose that the very fabric of space-time rotates like a cosmic whirlpool, dragging the CMB into alignment. If true, this would mean the Big Bang wasn't the absolute beginning but part of a larger, unseen process. But not everyone's convinced. Skeptics argue it could just be an illusion, a trick of how we're observing the universe. Our solar system moves through the cosmos at over 1 million miles per hour, and this motion might distort the CMB in ways we don't fully understand. Or perhaps galactic dust is screening parts of the signal, creating false patterns. Yet after years of analysis, no mundane explanation has fully erased the anomaly. The stakes couldn't be higher. If the axis of evil is real, it hints at physics beyond our standard models, a shadow of something vast and ancient lurking just beyond our understanding. It's a reminder that even our most precise maps of the cosmos might still be missing the biggest picture of all. Dark energy has been pushing the cosmos apart for billions of years. But what if that acceleration isn't just steady, but growing stronger over time? This is the terrifying premise of phantom energy, a hypothetical form of dark energy so extreme it wouldn't just expand the universe, it would ultimately shred spacetime itself in an apocalyptic event cosmologists call the Big Rip. Unlike the gradual fading of heat death or the dramatic collapse of a big crunch, This scenario spells a violent, literal end to reality as every structure, from galaxy clusters to atoms, gets torn apart by the universe's own accelerating expansion. The math behind phantom energy is as simple as it is unsettling. In standard cosmology, dark energy's strength is represented by a parameter called W, the equation of state. For normal dark energy, the kind we think exists today, W equals -1, but phantom energy takes this further, with W dipping below -1, meaning its repulsive force doesn't just persist, it intensifies as space stretches. Picture a car's gas pedal getting stuck. At first, you accelerate gradually, but soon you're hurtling uncontrollably. Now imagine that pedal controls the fabric of reality. Here's how the end would unfold. Roughly 60 million years before doomsday, the accelerating expansion would rip galaxies apart, sending stars adrift into the void. 3 months prior, solar systems would disintegrate as planets lose their gravitational anchors. In the final minutes, stars and planets themselves would explode as the phantom energy's grip overcomes the forces binding their matter together. Then, in the last unimaginable instance, atoms, the building blocks of everything, would be torn asunder as even the nuclear strong force succumbs. Space-time itself would fracture, leaving not emptiness, but a reality where concepts like distance and time cease to have meaning. But how soon could this happen? Calculations suggest that if phantom energy exists, the big rip might occur in as little as 22 billion years, a blink in cosmic terms. Some models even propose we could detect its early signatures within decades, as the stretching of space-time subtly alters how light from distant supernova reaches us. The most haunting implication: if phantom energy is real, there's no escape. No technology could outrun the expansion, as the rip would surpass light speed itself. It's a reminder that the universe's fate might not be a slow fade, but a crescendo of destruction, one where even the fabric of existence isn't safe from its own dark energy's hunger. If black holes are the universe's ultimate drains, swallowing everything that crosses their path, then white holes might be their cosmic opposites, mythical fountains spewing out matter and light with unstoppable force. While black holes trap even light behind an event horizon, white holes would theoretically repel all matter, forbidding anything from entering while violently ejecting energy outward. They're like the universe's fire alarm, blasting energy into space without any way to turn them off. The idea traces back to Einstein's equations of general relativity, which mathematically allow for white holes as valid solutions, just as they predict black holes. But while we've observed black holes littering the cosmos, white holes remain purely hypothetical ghosts in the machinery of physics. What would a white hole actually look like? Picture a region of space where matter and energy erupt like a geyser, shooting outward at impossible speeds. Unlike a black hole's silent pull, a white hole's expulsion would be violent and bright, potentially explaining some of the most energetic explosions in the universe. Some theorists speculate that gamma-ray bursts, those fleeting but hyperluminous flashes detected across the cosmos, could be white holes briefly flaring into existence before vanishing. Others propose that white holes might resemble quasars in reverse, glowing not from infalling material but from an internal pressure cooker of space-time itself. The most compelling twist: white holes might not just be black holes' opposites, they could be their aftermath. In loop quantum gravity, a framework aiming to unify general relativity with quantum mechanics, black holes might not crush matter into singularities forever. Instead, as a black hole evaporates via Hawking radiation, the extreme quantum effects at its core could cause it to bounce, rebounding as a white hole. In this scenario, every black hole could one day transform into a white hole, turning cosmic destruction into creation. Imagine a star collapsing into a black hole, only to re-emerge millions or billions of years later as a fountain of new particles, a cosmic phoenix rising from its own gravitational ashes. Yet the hurdles are daunting. For white holes to exist, they'd need a mechanism to prevent matter from falling in, violating the second law of thermodynamics by seemingly decreasing entropy. Some models suggest that white holes could only form in the early universe or as part of quantum foam, the frothy space-time turbulence at the smallest scales. Others argue they're mathematical curiosities with no physical reality, like time-reversed echoes of black holes that can't manifest in our forward arrow universe. The search for answers isn't just academic. If white holes exist, they'd offer a window into quantum gravity's deepest mysteries, how space-time behaves when stretched to its limits. They might even explain the Big Bang itself, with some theories proposing our universe erupted from a primordial white hole's explosive birth. Until we detect one, though, they remain tantalizing what-ifs, reminding us that the cosmos still holds paradoxes even Einstein couldn't resolve. And if we ever do find one, it wouldn't just rewrite physics, it would redefine our understanding of cosmic beginnings and endings. What if time itself could crystallize not into jewels, but into structures that pulse with motion forever, never winding down or needing energy to sustain them? Welcome to the bizarre world of time crystals, a concept so radical it redefines our understanding of order and motion in the universe. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns in space, time crystals are hypothetical structures whose atoms oscillate in a repeating cycle in time, creating a perpetual rhythm without any energy input. It sounds like a violation of the laws of physics, but in 2016, scientists actually created them in the lab, proving that under the right quantum conditions, the impossible becomes real. The genius behind time crystals lies in their defiance of equilibrium. Normally, everything in the universe tends toward a balanced, steady state. Think of a cup of coffee cooling to room temperature. But time crystals are different. Their atoms are locked in a never-ending dance, flipping between states like a metronome that never winds down. This isn't just a quirk of quantum mechanics, it's a new phase of matter, one where the arrow of time itself seems to twist into a loop. Now imagine scaling this up to cosmic proportions. What if the universe itself is a kind of time crystal, with the fabric of space-time oscillating in an eternal pattern? Some theorists suggest that the Big Bang might not have been a one-time event, but part of a grander cycle, a cosmic heartbeat where expansion and contraction repeat across eons. In this view, dark energy's accelerating push and gravity's pull could be the universe's way of ticking, with each cycle birthing a new iteration of reality. The implications are staggering. A time crystal universe wouldn't need an external clock or a beginning in the traditional sense. It would be self-sustaining, a closed loop of cause and effect where the end feeds back into the start. Think of it like a Möbius strip where time has no true starting point, just an endless, repeating corridor. This could solve one of cosmology's biggest mysteries, why time seems to flow in one direction. In a time crystal cosmos, the arrow of time might not be fundamental but emergent, a side effect of these larger cyclical patterns. But how could we test such a wild idea? Some clues might lie in the cosmic microwave background. If the universe is a time crystal, its oscillations could leave faint imprints in the afterglow of the Big Bang, like echoes of a grander rhythm. Others suggest that gravitational wave detectors could one day pick up subtle vibrations in space-time structure, hinting at this underlying pulse. For now, time crystals remain mostly confined to lab experiments and theoretical models. Yet their very existence hints at a universe far stranger than we've dared to imagine, one where time isn't a river but a kaleidoscope, and where the cosmos might not just exist in time but be time itself. And if that's true, reality isn't just unfolding, it's dancing. What if gravity isn't a fundamental force at all, but a side effect of something far deeper, a cosmic mirage emerging from the hidden chaos of particles and information? This is the radical premise of entropic gravity, a theory that flips our understanding of gravity on its head. Forget Newton's apple or Einstein's warped spacetime here. Gravity arises from entropy, the universe's tendency toward disorder, playing out on invisible holographic screens that encode the fabric of reality itself. The idea comes from physicist Eric Verland, who in 2010 proposed that gravity might not be a force in the traditional sense, but an emergent phenomenon, a statistical consequence of microscopic interactions, much like temperature emerges from the motion of atoms. At its core, entropic gravity suggests that what we perceive as gravitational attraction is actually the universe's way of maximizing entropy on surfaces called holographic screens. These aren't physical barriers, but hypothetical boundaries where information about the distribution of matter gets encoded, like cosmic hard drives storing the data of reality. Imagine a room filled with gas. Left alone, the gas spreads evenly, maximizing entropy. Now place a divider with a small hole in it. Particles will naturally flow through the hole until equilibrium is restored. Verland's insight was that gravity might work similarly. When matter like a star or planet disturbs the entropy of these holographic screens, the system responds by pushing toward equilibrium, creating what we experience as gravitational pull. It's not that masses attract each other. It's that the universe is constantly reorganizing information to stay as disordered as possible, and gravity is the byproduct. This framework does more than redefine gravity. It bridges quantum mechanics and general relativity, two theories famously at odds. In Verland's model, spacetime itself emerges from the entanglement of quantum bits on these holographic screens, mirroring the holographic principle's claim that reality might be a projection from a lower dimensional surface. If correct, it would mean that spacetime isn't the stage physics happens on, it's the play itself, an emergent script written by quantum information, but the boldest claim. Entropic gravity could explain dark matter without invoking unseen particles. Verland argues that what we attribute to dark matter's gravitational effects might actually be the result of entropy's influence on galactic scales. When applied to galaxy rotation curves, his equations reproduce observations without requiring mysterious, invisible matter, a tantalizing solution to one of cosmology's biggest puzzles. Skeptics point out gaps, the math remains speculative, and experiments haven't yet confirmed deviations from Einstein's predictions in weak gravitational fields, where entropic gravity should differ. Yet the theory's elegance keeps it alive, challenging us to consider that gravity might not be woven into the universe's fabric, but etched onto its surface, a holographic illusion waiting to be decoded. What if the universe has a hidden twin, a mirror version of reality where everything is flipped from the spin of particles to the flow of time itself? This is the tantalizing premise of the mirror universe theory, a radical idea suggesting that dark matter might not be made of exotic particles at all, but of ordinary matter from a parallel cosmos governed by reversed physics. Imagine a world where your reflection isn't just an image, it's a whole other reality, invisible yet intertwined with our own, its presence only betrayed by the gravitational tug we call dark matter. The roots of this theory trace back to one of physics' most elegant principles, symmetry. Nature loves balance, positive and negative charges, matter and antimatter, even the way particles behave when you flip them in a mirror. But there's a catch. When scientists study subatomic particles, they find that some symmetries are broken. Take neutrinos, those ghostly particles that stream through the universe almost unnoticed. They oscillate between different types, electron, muon, and tau neutrinos as they travel, a phenomenon that hints they might have mass. But here's the puzzle. The way they oscillate doesn't perfectly mirror the behavior of their antimatter counterparts. This asymmetry suggests that somewhere a hidden partner might be tipping the scales. Enter the mirror universe. If a shadow cosmos exists where the laws of physics are flipped, right-handed particles dominate, and time might even flow backward, it could explain not just neutrino oddities but the very nature of dark matter. In this mirrored realm, stars and galaxies made of mirror matter would pass through ours like phantoms, interacting only via gravity. That means we'd feel their mass but never see their light, exactly as we observe with dark matter's ghostly influence on galactic rotations and cosmic structures. The math behind this idea is surprisingly elegant. Mirror particles wouldn't need new forces or undiscovered physics, just a tweak to existing symmetries. For every proton in our world, there could be a mirror proton, its spin reversed and its interactions perfectly balanced against ours. Collisions between ordinary and mirror particles would be vanishingly rare, explaining why dark matter seems to ignore everything but gravity. Even neutrinos' oscillations could be a whisper of this duality, a subtle handshake between realities. Could we ever detect this mirror realm? Some experiments are already searching. When neutrons are trapped in magnetic fields, they sometimes vanish for fractions of a second, as if slipping into another dimension. Theorists suggest they might be tunneling into the mirror universe and back. Other clues could hide in the cosmic microwave background, where anomalies in temperature fluctuations might reveal gravitational imprints from mirror galaxies brushing against ours. The implications are staggering. If true, the mirror universe wouldn't just solve the dark matter puzzle. It would mean we're living in one half of a cosmic double helix, our reality perpetually balanced against its unseen twin. And somewhere out there, another version of physics might be writing its own rules, forever just beyond our reach. At the heart of every black hole lies a mystery, a singularity where gravity crushes matter into an infinitely dense point and physics as we know it breaks down. But what if singularities aren't the end? What if, hidden behind the event horizon, black holes transform into something even more bizarre, rebounding into unimaginably dense objects called Planck stars? This theory rewrites the final act of a black hole's life, suggesting that quantum effects could halt total collapse and trigger a cosmic bounce, turning destruction into rebirth. The key lies in the clash between general relativity and quantum mechanics. Einstein's theory predicts that collapsing matter will squeeze endlessly into a singularity, but quantum physics abhors infinity. It suggests that at the smallest scales, spacetime becomes granular, like pixels on a screen. When a dying star's core reaches this scale, known as the Planck length, quantum gravity might kick in like a cosmic trampoline, reversing the collapse. The result, a Planck star, an object with the mass of a black hole compressed into a volume trillions of times smaller than an atom, yet not quite a singularity. It's the universe hitting a hard stop and bouncing back, like a ball thrown against a wall with perfect elasticity. Now contrast this with Hawking radiation, the slow leak of energy that causes black holes to evaporate over eons. In Hawking's model, information swallowed by a black hole seems lost forever, violating quantum mechanics' rule that information can't be destroyed. This information paradox has haunted physicists for decades. But Planck stars offer a way out. If black holes rebound into these ultra-dense remnants, information might not vanish. It could be trapped inside the Planck star's fiery core, preserved until the star itself radiates away. Think of it like a book burned to ash. Hawking's version scatters the ashes to the wind, making reconstruction impossible, while the Planck star keeps the ashes in a sealed jar, waiting to be pieced back together. The implications are staggering. Planck stars could solve multiple cosmic puzzles at once, from the information paradox to the nature of quantum gravity. They might even leave observable traces. Some theorists suggest that when a Planck star finally explodes after eons of slow evaporation, it could release a burst of gamma rays or gravitational waves, a last shout from a reborn black hole. Telescopes hunting for unexplained flashes in the distant universe might one day catch this signature, offering proof that black holes aren't eternal prisons but stages in a grander cycle. Yet the wildest possibility isn't just about black holes, it's about the universe itself. If matter can rebound from total collapse, could the Big Bang have been the bounce of a previous cosmos? Planck stars hint at a deeper truth, that destruction and creation might be two sides of the same coin, spinning endlessly in the dark. After all, if a black hole's death can seed new physics, who's to say our entire universe wasn't born from something similar? The answer might be written in the quantum echoes of those rebounding stars, if only we could listen closely enough. Einstein once dismissed quantum entanglement as spooky action at a distance. But what if that spookiness is actually the universe threading itself together through microscopic wormholes? This is the radical promise of the ER=EPR conjecture, a theory that dares to merge two of physics' most mind-bending concepts, wormholes and quantum entanglement. At first glance, they couldn't seem more different. Wormholes, or Einstein-Rosen bridges, are cosmic shortcuts through spacetime, tunnels that could theoretically connect distant regions of the universe or even different universes. Entanglement, on the other hand, describes how particles can become linked across vast distances, instantly influencing each other's states no matter how far apart they are. Yet in 2013, physicists Juan Maldeisner and Leonard Susskind proposed these phenomena might be two sides of the same coin, that every pair of entangled particles is invisibly connected by a tiny wormhole, stitching the fabric of reality together from the inside out. Picture two electrons created together in a lab, then flung to opposite sides of the galaxy. Measure one's spin as up, and the other instantly becomes down, defying the speed of light. Normally, we'd call this magic or bad physics, but if a microscopic wormhole threads between them, that connection makes eerie sense. The wormhole wouldn't be a traversable tunnel like in sci-fi. It'd be more like a quantum umbilical cord, allowing information to sync without ever crossing the space in between. It's as if the universe, when faced with the paradox of entanglement, cheated by folding spacetime into a hidden loop behind the scenes. This idea didn't come from nowhere. Black hole physics had long hinted at a deep link between spacetime geometry and quantum information. When matter falls into a black hole, its information gets scrambled and radiated back out as Hawking radiation, a process that mathematically resembles quantum teleportation through a wormhole. Maldeisner and Susskind took this further, arguing that entanglement and wormholes might be dual descriptions of the same underlying reality. In their framework, the more entangled two systems are, the more connected their spacetime geometry becomes, like invisible threads tightening the cosmic tapestry. The implications rewrite our understanding of reality. If ER=EPR holds, then quantum mechanics and gravity, the two pillars of modern physics that have resisted unification for a century, might be deeply intertwined. Spacetime itself could emerge from a vast network of entanglement, woven together by countless microscopic wormholes like threads in a cosmic quilt. This would mean the universe isn't just held together by gravity or chance, but by an invisible architecture of quantum connections, each one a stitch in the fabric of existence. Could we ever test this, some clues might lie in the physics of black holes. If entangled particles are indeed linked by wormholes, then manipulating one particle in a lab might create measurable effects on spacetime geometry at microscopic scales. Others suggest that advanced quantum computers could simulate wormhole dynamics, offering indirect proof. For now, the conjecture remains a dazzling hypothesis, but one that dares us to imagine a universe where the spookiest quantum phenomena might just be gravity in disguise, whispering its secrets through hidden tunnels in the dark. The smooth, continuous fabric of spacetime we take for granted might be nothing more than an illusion, a cosmic mirage concealing a far stranger truth beneath. Enter the causal sets approach, a radical reimagining of reality where spacetime isn't a flowing river but a shimmering digital mosaic, built from tiny, indivisible atoms of causality. Imagine the universe as an intricate network of moments, each one linked to others in a vast web of cause and effect, with no smooth transitions, just discrete, granular steps like frames in a cosmic film reel. This isn't just a philosophical tweak, it's a full-throated revolt against the infinite densities and warped geometries of Einstein's relativity, offering a way to quantize gravity itself while banishing the nightmares of singularities forever. The heart of this idea lies in a simple but profound shift. Space-time isn't fundamental. Instead, it emerges from something deeper, a lattice of elementary events ordered by which events influence others. Picture a domino rally where each tile represents a moment in space-time, and the chain reaction of their falls defines the arrow of time. But here's the twist: the dominoes don't exist in space, they create space by the way they're arranged. This means that what we perceive as distance or duration isn't baked into the universe, it's a side effect of how these causal relationships stack up. The result, a cosmos where space-time is pixelated at the smallest scales, with no room for the infinitely dense singularities that plague black holes or the Big Bang. Why does this matter? Because singularities aren't just mathematical oddities, they're where physics breaks down completely. In Einstein's equations, black holes crush matter into points of infinite density, and the Big Bang erupts from an infinitely hot, infinitely small speck. But infinities don't exist in nature. They're red flags signaling our theories are incomplete. Causal sets sweep them aside by replacing the smooth continuum of relativity with a discrete structure. There's no infinitely small here, just the smallest possible unit of spacetime, a single atom in the cosmic chain. When matter collapses, it doesn't vanish into a singularity. It reaches a final, finite density and stops, like a pixelated image hitting its resolution limit. The implications ripple outward. If spacetime is granular, then gravity, the last holdout resisting quantization, might finally unite with quantum mechanics. In this framework, gravity isn't a force warping a smooth backdrop. It's the statistical jitter of these causal connections, like the buzz of static between TV pixels. Some models even suggest that the cosmic expansion we attribute to dark energy could stem from new causal links constantly forming, stretching the network from within. But how could we ever test such an abstract idea? Surprisingly, there might be clues in the sky. If spacetime is discrete, high-energy photons from distant gamma-ray bursts could arrive at Earth slightly out of sync, their travel times nudged by the universe's underlying pixelation. Experiments like the Fermi Gamma-Ray Space Telescope are already hunting for these tiny delays. Others probe the fabric of reality using ultra-precise atomic clocks, watching for minute fluctuations that betray spacetime's granularity. The causal set's approach isn't just a technical fix, it's a philosophical upheaval. It suggests that time might not flow but unfold, like a cosmic algorithm processing events one step at a time. That the universe isn't a stage but a story written in the language of cause and effect. And if it's right, the greatest mysteries, from black holes to the Big Bang, might not be walls but doorways waiting to be unlocked by the key of causality itself. What if reality only exists because we're here to witness it? The observer effect in quantum mechanics reveals something startling: particles don't settle into definite states until they're measured. It's as if the universe holds its breath, waiting for a conscious observer to collapse endless possibilities into a single outcome. This isn't just a quirk of tiny particles, it might be the key to the cosmos itself. Welcome to the observer's theory, where consciousness isn't a passive bystander but the architect of reality, weaving the universe into existence one observation at a time. The roots of this idea stretch back to the double-slit experiment, where particles behave like waves when unobserved but snap into crisp, pinpoint locations the moment someone looks. Physicists like John Wheeler took this further, proposing that observers, whether humans, animals, or even advanced AI, are essential participants in creation. In his participatory universe model, the Big Bang didn't just happen 13.8 billion years ago. It's happening now, retroactively crystallized by every act of observation. Picture a cosmic game of 20 questions where the universe asks, "Did you mean this?" each time we measure it, shaping history to fit our answers. This loops eerily into the anthropic principle, the notion that the universe's laws appear fine-tuned for life because, well, we're here to notice. But the observers takes it further. What if the fine-tuning isn't accidental but intentional, with consciousness sculpting physics to allow its own existence? Imagine a painter who only emerges because the painting they're creating permits it. A self-fulfilling cosmic loop where observers and the observed define each other. Critics argue this veers into philosophy, but some quantum interpretations lend it weight. Von Neumann-Wigner theory posits that consciousness causes wave function collapse, while cubism treats quantum probabilities as subjective beliefs. Even the multiverse gets tangled in this. In Everett's many worlds, every observation splits reality, suggesting consciousness isn't just shaping worlds, it's multiplying them. The implications are dizzying. If consciousness molds reality, does a tree falling in an empty forest make a sound? Or does the forest itself flicker between potential states until a mind arrives to hear it? And what about AI? Could a sufficiently advanced machine become a cosmic co-creator? Some experiments, like delayed choice quantum erasers, hint at retroactive causality where present observations rewrite the past's possibilities. Yet the grandest question remains, are we the universe's accidental guests or its reason for being? The observers doesn't just blur the line between observer and observed, it suggests the line was never there to begin with. Reality might not be a stage we walk onto, but a dance we're choreographing with every thought, every glance, every act of attention. And if that's true, then the greatest mystery isn't how the universe created consciousness, but how consciousness keeps creating the universe. Deep in the cosmos, astronomers have found something that shouldn't exist, a river of galaxies streaming relentlessly toward the edge of the known universe, as if pulled by some unseen force beyond our cosmic horizon. They call it the dark flow, a mysterious collective motion of galaxy clusters racing at over 2 million miles per hour toward a single patch of sky. This isn't the expected expansion from the Big Bang. It's a coordinated migration, like iron filings drawn to a hidden magnet, and the most unsettling explanation. The gravitational tug of another universe, one lying beyond the reach of our telescopes, warping space-time in ways we can't yet see. The discovery first shocked scientists in 2008, when researchers studying the cosmic microwave background noticed an anomaly. Galaxy clusters weren't just drifting apart with the universe's expansion, they showed a peculiar bulk motion, a current flowing toward the constellations Centaurus and Hydra. The scale was staggering, hundreds of clusters, some billions of light-years apart, all moving in sync across vast cosmic distances. Normal physics couldn't explain it. Gravity from visible matter wouldn't be strong enough, and dark matter's pull should be evenly distributed, not focused in one direction. It was as if the universe itself was leaning toward something just out of sight. One radical theory suggests this flow might be evidence of a parallel universe, a neighboring bubble in the multiverse whose gravity leaks into ours. Picture two soap bubbles floating close together. Though their surfaces don't touch, the space between them warps slightly, creating a subtle pull. If another universe exists beyond our cosmological horizon, its mass could be distorting space-time on scales we can't directly observe, dragging our galaxy clusters along like leaves caught in a cosmic undertow. But skeptics push back. Could the dark flow just be an illusion, a trick of incomplete data or measurement errors? When the Planck satellite mapped the CMB with higher precision, the signal persisted, but with weaker statistical significance. Some argue that the flow might originate from a gargantuan, unseen structure within our own universe, like a supercluster of galaxies so vast it defies current models. Others propose exotic physics, like modifications to Einstein's theory of gravity on cosmic scales. The wildest possibility, the dark flow might not be motion at all, but a relic of the universe's birth. If the Big Bang wasn't perfectly uniform, primordial imbalances in space-time could have left behind tilted regions where gravity still carries echoes of that initial lopsidedness. It's like rolling a lumped ball of dough. Even as it expands, some parts retain hidden density, tugging everything slightly off-center. For now, the dark flow remains one of cosmology's most tantalizing puzzles. Future telescopes like the Euclid Space Observatory could settle the debate by mapping galaxy motions with unprecedented detail. If the flow is real, and if it points to another universe, it would be the first experimental hint of a reality beyond our own, a cosmic neighbor forever out of reach, yet close enough to pull us toward the unknown. Until then, this mysterious current serves as a humbling reminder. The universe may not just be larger than we imagined, but stranger than we've dared to dream. At the heart of a neutron star, matter doesn't just bend the rules of physics, it shreds them entirely. These cosmic remnants, forged in the violent collapse of massive stars, squeeze more mass than our sun into a sphere the size of Manhattan, creating densities so extreme that a single teaspoon of their material would weigh billions of tons on Earth. The surface gravity is strong enough to warp light into a hall of mirrors, and magnetic fields a trillion times stronger than Earth's crackle through the vacuum. But what if these hellish environments aren't just lifeless wastelands? What if, buried beneath the crushing gravity and searing radiation, neutron stars host civilizations so advanced they've turned the star's very crust into their habitat? This is the neutron star life hypothesis, a daring speculation that intelligent life might not just survive in such extremes, it could thrive by repurposing the star's own incomprehensible physics. Imagine a society that evolved not on planets, but in the nuclear furnace of a neutron star's crust, where mountains no taller than a millimeter are denser than all the skyscrapers on Earth combined. These microscopic peaks, formed by the star's insane gravity and magnetic stresses, could serve as the ultimate computational substrate. In a neutron star's crust, atomic nuclei are packed so tightly they arrange into bizarre shapes: rods, plates, even spaghetti like strands physicists call nuclear pasta. To us, this sounds like chaos. To a neutron star civilization, it might be the equivalent of silicon for microchips, a natural lattice for processing information at speeds unimaginable to our sluggish, chemical-based brains. The energy sources available would dwarf anything on Earth. A single magnetic field line snapping and reconnecting could power a civilization for millennia, while the star's thermal glow, a blistering 1,000,000 degrees, could be harvested like sunlight. Communication might happen through vibrations in the crust or modulated gamma-ray pulses, bypassing the need for radio waves that'd be instantly drowned in the star's electromagnetic roar. And time itself would flow differently here. A neutron star's gravity slows clocks to a crawl compared to the wider universe. A decade for them might be a century for us, allowing their technology to evolve at a pace we can't fathom. But how could life even arise in such conditions? Earth-like biology is impossible here. No molecules could survive the pressure, and chemistry as we know it ceases to exist. Yet alternative biologies might emerge from pure nuclear interactions. Hypothetical nucleic creatures could be built from tightly bound clusters of quarks or strange matter, their thought processes unfolding through quantum tunneling rather than electrical signals. Their cells might be bubbles of quark-gluon plasma, stabilized by the star's crushing gravity. To them, our fleshy, carbon-based existence would seem as fragile as a soap bubble in a hurricane. The wildest implication, we might have already detected them, or rather, their infrastructure. Neutron stars sometimes exhibit glitches, sudden jumps in their rotation rate that defy conventional explanations. While most astrophysicists attribute these to cracks in the star's crust or superconducting fluids beneath, some have playfully speculated they could be signs of massive energy use, like a civilization briefly diverting the star's spin to power a project. Even pulsar signals, those eerily precise cosmic lighthouses, could theoretically encode artificial patterns, though no such evidence has been found. Of course, this remains the realm of extreme speculation. The sheer violence of a neutron star's environment seems inimical to any form of complexity, let alone intelligence. But if there's one lesson from the history of science, it's that life adapts to the unlikeliest niches. And if civilizations do exist there, they'd be so far beyond our understanding that their very existence might rewrite what we consider possible. After all, to a species born in a nuclear inferno, the idea of life on a gentle, watery planet like Earth might sound just as absurd. The universe might seem stable, its laws constant, its structures enduring, but beneath this illusion of permanence lies a chilling possibility. The entire cosmos could be perched on the edge of annihilation, waiting for a random quantum fluctuation to tip it into oblivion. This is the vacuum metastability event, a scenario where the very fabric of reality could be rewritten in an instant, not by a cosmic collision or a black hole's hunger, but by a tiny, spontaneous quantum bubble that erupts with the force of a new Big Bang. At the heart of this theory lies the Higgs field, an invisible energy field that permeates all of space, giving particles their mass. We've measured it, tested it, and confirmed its existence, but what if it's not in its true lowest energy state? Think of the Higgs field like a marble resting in a shallow valley on a vast, undulating hillside. The valley isn't the lowest point, it's just a local dip, and with enough energy, the marble could roll out, tumbling downhill into a far deeper valley. If that happened, the Higgs field's new state would rewrite the rules of physics, altering the masses of particles, the strength of forces, even the nature of spacetime itself. The result, a wave of destruction propagating at the speed of light, erasing atoms, stars, and life as we know it before we could even blink. How likely is this doomsday scenario? Surprisingly, the math doesn't rule it out. Calculations suggest our universe's Higgs field is in a metastable state, not perfectly stable, but not immediately prone to collapse either. The estimated timescale for a spontaneous quantum fluctuation to trigger this event, somewhere between 10 to the power of 100 years and never. Those odds might seem comforting, but here's the catch. All it takes is one tiny nudge in the wrong place at the wrong time. High-energy events like a supernova's shockwave or particle collisions in a futuristic accelerator could theoretically provide that nudge, creating a bubble of true vacuum where the laws of physics are unrecognizable. The most unsettling part, we might never see it coming. The bubble's boundary would expand at light speed, leaving no warning. One moment, the universe operates as usual. The next, an advancing wall of rewritten physics obliterates everything in its path. Some theorists argue this could already be happening somewhere in the cosmos, with a death wave racing toward us right now. Others counter that the sheer size of the universe makes it statistically improbable, but improbable doesn't mean impossible. Yet there's a twist. This apocalyptic scenario might also be a creative force. If a vacuum metastability event occurred in isolation, it could birth an entirely new universe with its own laws, separate from ours. In this view, our cosmos might itself be the product of such a bubble, a cosmic reset button pressed by some long-forgotten quantum accident. The question isn't just whether our universe is fragile, it's whether fragility might be the engine of cosmic evolution, where each collapse seeds a new beginning. For now, the vacuum metastability event remains a terrifying what-if, a reminder that even the most fundamental rules of reality might be temporary. And if the math holds, it means the universe isn't just unpredictable, it's a quantum roulette wheel, spinning silently in the dark. Imagine a world where magnets couldn't exist, where every North Pole came glued to a South Pole, inseparable like two sides of a coin. That's our reality, but in 1931, physicist Paul Dirac shattered this assumption with a bombshell prediction. magnetic monopoles, hypothetical particles carrying just a single magnetic charge, like an electron but for magnetism. These elusive entities would rewrite physics overnight if they existed. Yet despite decades of searching, from deep underground labs to cosmic ray detectors, not a single monopole has been found. Their absence isn't just a curiosity, it's a crisis for our deepest theories of the universe, exposing cracks in our understanding of how forces unite at the dawn of time. Dirac's logic was elegant. Just as electric charges exist independently, think protons and electrons, why couldn't magnetic ones? His equations revealed a startling symmetry. If even one monopole lurked in the cosmos, it would explain why electric charge comes in fixed quantized units. The math was so compelling that Nobel laureate Julian Schwinger later quipped, "Monopoles are theoretically too beautiful to not exist, but beauty alone doesn't guarantee reality." The hunt for monopoles became a saga of false hopes, from an infamous 1982 experiment where one candidate signal turned out to be a lab technician's screwdriver left on the detector, to cosmic ray searches that came up empty-handed. The stakes skyrocketed with the rise of grand unified theories, or GUT, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework. These theories demand monopoles as cosmic relics from the universe's first trillionth of a second, when symmetries shattered like glass and left topological defects in spacetime, knots of energy that became monopoles. According to JUTs, the early universe should have produced them in staggering numbers, enough that we'd trip over them daily. So where are they? One possibility is inflation, the universe's explosive growth spurt right after the Big Bang. If inflation stretched spacetime exponentially, it could have diluted monopoles to near zero density, scattering them so thinly they're virtually undetectable. It's a neat fix, but it feels like moving the goalposts, solving one mystery by invoking another. Others propose monopoles are hiding in plain sight, masquerading as primordial black holes or tucked away in extra dimensions. The wildest idea, monopoles did dominate the early universe but decayed into other particles, leaving behind faint traces in cosmic rays or neutrino detectors. Yet the most unsettling implication of their absence isn't about monopoles at all, it's what their absence says about us. Every failed search forces physicists to ask, are our grand unified theories fundamentally flawed? Is the universe withholding a symmetry we're certain must be there? Or could monopoles be so exotic, emerging only in fleeting high-energy collisions or bound to dark matter, that we've been searching all the wrong places? For now, the monopole remains a ghost in the equations, a shadow of a universe that might have been. But the search isn't over. Cutting-edge experiments like Mo-Edel at CERN and IceCube in Antarctica are probing extreme energies and cosmic particles for signatures. If found, monopoles wouldn't just complete Dirac's vision, they'd be living fossils from the universe's first moments, keys to unlocking the forces that shaped everything. And if they're truly gone, then the cosmos might be far stranger and far less symmetrical than we ever dared to imagine. Einstein's equations allowed for a universe where time itself could twist into a loop, a cosmos not just expanding but spinning like a vast cosmic carousel. This is the Gödel universe, a mind-bending solution to general relativity discovered in 1949 by mathematician Kurt Gödel. His model wasn't just mathematically elegant, it was a direct challenge to our most intuitive sense of reality, proving that under the right conditions, time travel isn't just science fiction, it's baked into the fabric of spacetime itself. Imagine a universe where every star, every galaxy is caught in a slow, relentless whirlpool. In Gödel's cosmos, this rotation isn't just motion, it's a fundamental feature that warps causality. The math reveals that if you set off in a straight line, tracing the curve of spacetime, you could eventually return to your starting point not just in space, but in time, arriving before you ever left. These closed time-like curves, as they're called, aren't mere hypotheticals. They're inevitable consequences of the universe's rotation, like eddies in a flowing river. Gödel's brilliance lay in showing that such a universe wouldn't violate relativity. In fact, it fit Einstein's equations perfectly. The rotation creates a centrifugal force that balances gravity, preventing collapse, while the twisted spacetime geometry allows for paths that loop back on themselves. It's as if the universe is a Möbius strip of time where cause and effect stutter and repeat. The implications are staggering. Free will becomes a puzzle, history a tangled web, and the future might already be written in the past. Yet the Gödel universe isn't just a playground for philosophers. It forces physicists to confront the limits of our cosmic models. Our own universe shows no signs of large-scale rotation galaxy spin, but the cosmos as a whole seems to lack the angular momentum needed for Gödel's time loops. But what if rotation isn't zero, just vanishingly small? Or what if pockets of extreme rotation exist locally, hidden in the gravitational wake of supermassive black holes? Some theories even suggest that advanced civilizations could engineer Gödel-like conditions, creating artificial time loops for reasons beyond our comprehension. The most haunting question remains: if time travel is mathematically possible in some universes, does that mean it's possible in ours? Gödel himself grappled with this, arguing that the existence of such models undermines the objectivity of time. Einstein, unsettled by the implications, called it a problem that troubled him deeply. For all its elegance, the Gödel universe serves as a humbling reminder that the cosmos might not just be stranger than we imagine. It might be stranger than we can imagine, with time itself a fluid construct waiting to be rewoven. What if the universe isn't just heading toward heat death or collapse but awakening? The omega point theory isn't just another cosmic finale. It's a vision of the universe's ultimate transcendence, a moment where consciousness and physics merge into something beyond imagination. Picture this, trillions of years from now, as the cosmos contracts or evolves toward its final state. Every thought, every mind, every spark of intelligence converges into a single, luminous point of infinite complexity, the omega point. This isn't science fiction. It's a daring synthesis of theology, cosmology, and transhumanism, suggesting that the universe's destiny isn't oblivion but a kind of cosmic enlightenment. The roots of this idea trace back to Pierre Teilhard de Chardin, a Jesuit priest and paleontologist who saw evolution as a spiritual journey. In the 1920s, he proposed that the universe was evolving toward a divine apex, the omega point, where all consciousness would unite in a supreme form of awareness. To Teilhard, this wasn't metaphor but physics. Evolution had direction, and its endpoint was God. Fast forward to the 20th century, and physicist Frank Tipler reimagined Teilhard's vision through the lens of hard science. In Tipler's omega point cosmology, the universe's far future, whether through infinite expansion or a final collapse, would create the conditions for an all-knowing, all-powerful computational singularity. Here's how it might unfold. If the cosmos collapses in a big crunch, advanced civilizations could harness the energy of collapsing stars to perform infinite computations, growing exponentially smarter as spacetime shrinks. Minds would merge, simulating every possible experience, every configuration of matter, until all knowledge and consciousness fuse into a single, omnipotent entity. Even in an eternally expanding universe, Tipler argues, civilizations could use black holes as quantum computers, racing against the heat death to simulate an infinite existence before entropy wins. The end result, a universe that doesn't just fizzle out, it wakes up. The implications ripple across disciplines. For transhumanists, the omega point isn't mystical, it's technological. Think of it as the ultimate singularity, where AI and post-human intelligence engineer their own salvation, bending physics to escape entropy's grip. Some even speculate that we might already be simulations running in the omega point's vast historical archive, reliving our lives as data points in its cosmic memory. Theologians, meanwhile, debate whether this entity would be indistinguishable from divinity, a god not of scripture but of pure information. But the theory isn't without critics. Physicists question whether infinite computation is possible, even with collapsing universes or black hole engines. Others argue that Tipler's assumptions about energy and intelligence stretch known physics to the breaking point. And then there's the haunting paradox. If the omega point knows everything, does that include simulating every possible suffering? Is paradise built on infinite pain? Yet the omega point endures because it dares to answer our deepest yearning that the universe has meaning, and that we're part of its grand finale. Whether as science, prophecy, or speculative fiction, it reframes existence as a story with a purpose, not a random flicker in the dark, but a spark destined to ignite the whole cosmic sky. And if it's right, the universe isn't just a machine, it's a cathedral, and we're the builders, the worshippers, and the final prayer all at once. From holographic projections stretching across cosmic horizons to black holes birthing entire universes, we've journeyed through theories that don't just push boundaries, they dissolve them entirely. Picture a reality where time crystallizes into repeating loops, where dark flow hints at unseen universes tugging at ours, or where the very act of observation might be stitching existence together. These aren't just abstract ideas, they're seismic shifts in how we understand space, time, and our place within it. Consider the sheer audacity of these concepts. The holographic principle suggests everything we see is a shadow cast by information encoded on the universe's edge. Cosmic strings could knot space-time into time-traveling highways. The simulation hypothesis forces us to question whether our emotions, memories, and the stars above are nothing more than lines of code in an unfathomable program. Each theory peels back another layer, revealing a cosmos far stranger and more interconnected than we ever imagined. But here's the most thrilling part: these aren't fantasies. They're testable, debated, and pursued by brilliant minds worldwide. The fact that we can even contemplate them, whether through math, telescopes, or quantum experiments, is a testament to human curiosity's boundless reach. Maybe one of these ideas will crack open the next great mystery. Maybe the truth is still out there, waiting for a future Einstein to uncover it. So which theory resonates with you? The eerie elegance of entropic gravity, the spine-tingling possibility of mirror matter, or the cosmic optimism of the omega point where the universe itself might awaken? Drop your favorite in the comments. Let's geek out over the possibilities together. And if your brain's buzzing for more deep dives into the universe's hidden layers, hit that subscribe button. This is just the beginning. The cosmos has countless secrets left to spill, and we'll be here to explore every one. Until next time, keep looking up and questioning everything.